So thank you and welcome everybody. In my talk today, I'm going to be presenting the technical details of OpenGL ES 2.0 so that you as developers will be ready for developing games for next generation 3D handsets that support GPU programmability. Before I begin, I just wanted to briefly introduce myself. My name is Dan Ginsberg, and I work in the 3D application research group at ATI on the handheld team, where I work on demos and tools for our handheld 3D graphics chips. Most recently, I worked on a demo for the launch of our Imagion 238X, which is our latest 3D handheld chip that supports OpenGL ES 1.1+. One little plug, if you guys are interested, I encourage you to stop by the ATI booth during the show, where we'll be showing a demo of that, as well as a port of an Xbox game named Sudeki running on the Imagion 238X. So with that said, I want to dive into ES 2.0, and let me begin with a couple of comments about the significance of ES 2.0. As many of you know, the spec was released in August of last year at SIGGRAPH, and since that time we've really seen widespread support for ES 2.0 for most of the major hardware players involved in creating 3D graphics for handheld devices. We've seen some actual announcements of hardware being developed and others just general support, but clearly ES 2.0 represents the future direction of 3D graphics in the handheld space. And the other thing that's really significant about ES 2.0 is that it really represents a convergence between desktop and handheld graphics functionality. It truly introduces the notion of GPU programmability onto handheld devices, and should mark a very important inflection point in the quality of graphics on handheld devices. So with that said, let me begin with the agenda of what I'll be talking about. First, I wanted to give an overview and history of OpenGL ES. And really the goal there is, I know many of you are probably very familiar with OpenGL ES, but I just want to set the context for the evolution of the spec and how we have arrived at ES 2.0 and GPU programmability. I'll try to do that briefly. After that, I'm going to really jump into the meat of my presentation, where I'm going to be talking about the technical details of ES 2.0, and I'm going to do that from basically three directions. First, I'll talk about shaders and how they fit into the programmable pipeline in ES 2.0. Then I'm going to talk about what's changed in the GL shading language relative to OpenGL on the desktop. So we'll look at what features were specifically added to the shading language for OpenGL ES and what's been removed. Then I'm going to talk about what's changed in the actual API itself aside from the shading language. So we'll look at what's different from OpenGL 2.0 on the desktop. And after that, the final part of my presentation, I kind of want to wrap everything up and talk about what do all of these changes mean for writing games for OpenGL ES 2.0, because as developers, it's really going to require somewhat of a shift in the way you develop your engines, and I want to talk about what some of those implications are. So I'll begin now with an overview and history of OpenGL ES. So what is ES? Again, as many of you probably know, it's an OpenGL-based API designed specifically for embedded systems. Embedded systems have a lot of constraints in terms of small form factor, low memory footprint, low power consumption. And what was done was to take OpenGL, the desktop API, to remove redundancy and expensive functionality as much as possible to enable implementations of ES on embedded devices. One of the goals of the spec was to keep it as compatible as possible with OpenGL so that apps could be easily ported between the two APIs, and also to leverage the existing tools and infrastructure that already exist for desktop OpenGL, as it's been around for many years. In addition, features were added that were needed specifically for embedded systems. For example, the introduction of fixed point for processors that don't have floating point. So you see a number of features that were added to the API to target these embedded devices. Who created OpenGL ES? It was created by the Khronos group, which is a nonprofit organization composed of over 100 companies now. The box in the middle are the promoting members of the Khronos group, and ATI, for our part, served as the spec editor on ES 1.1+ and also ES 2.0. So we've been very active in the Khronos group, but really it's been a group effort from many different companies and all of the major players in 3D graphics for handheld. So a little brief I wanted to say about why is OpenGL ES important. Clearly, we already see that it's the API of choice for 3D handheld games. We've seen implementations of OpenGL ES on Brew, on Symbian, on various devices, and there's already a lot of high caliber content being developed for OpenGL ES. But beyond that, ES 2.0 has implications beyond just the handheld space. For example, we see that OpenGL ES has served as the basis for the PlayStation 3's graphics library. And part of that is because ES 2.0 really represents the path forward for 3D in general. For one thing, it's a very lean and clean API, and it also allows for vendors to extend it in any way they see fit. That's one advantage it has over other APIs, is that vendors are free to create extensions to expose new hardware features that developers can use. And also, it really simplifies driver implementation by removing redundancy and expensive functionality. OpenGL ES essentially gets out of the way of developers, enables you to get close to the hardware without trying to do too much. And in general, that seems to be the path for 3D APIs. We see the same sort of thing with Direct3D 10, which has also removed fixed function and gone to full programmability. So, and then finally, I want to talk about the history of OpenGL ES, and then I'm going to move into the technical details. So, in 2004, the OpenGL ES 1.0 spec was released, and this was based on the desktop OpenGL 1.3 spec, and it was a fairly basic set of 3D functionality, although it has enabled very impressive content, but a lot was taken out to strip it down to enable an implementation on an embedded device. We then saw ES 1.1, and then the follow-on to that, the ES 1.1 extension pack, which I call 1.1 plus here, which is really a comprehensive set of fixed function 3D. Things like cube maps, matrix palette skinning, .3 bump mapping, all of the things we saw on fixed function devices on the desktop have now been added to ES 1.x. And that 1.1 plus was designed to be backwards compatible so that old games that were written for 1.0 would also run on it. Now, when the Khronos group got to trying to design shaders into the API for ES 2.0, they were really faced with a choice, which was, in general, one of the philosophies of the spec was to remove redundancy from the API wherever possible. But this created a problem for adding shaders because essentially anything you can do with fixed function programming, you can do with a shader. And so it didn't really make sense within that philosophy to have both fixed function and shaders in the same API. So what was done was that the Khronos group decided they would break backwards compatibility with previous versions of OpenGL ES and go to a fully programmable model. So you can really think now of ES 1.x and 2.x as completely separate APIs. Your games that are written for one are not going to run on the other without some significant porting effort. But it was really necessary to enable programmability without too much redundancy. So with that said, I want to now really dive into the details of OpenGL ES 2.0. And I'll start by talking about how shaders fit into the graphics pipeline. So first of all, the core of the API is formed by the OpenGL ES shading language, GLSL. And this is a subsetted language of desktop GLSL, but is mostly very similar. And I'll talk in a little bit about what the actual changes were for ES. One of the big things I want to mention right off the bat is that ES 2.0 does shift some of the programming burden from the driver to the application, because now you need to develop shaders to do the things that the driver used to do for you. For example, things that you're used to, like the matrix stack or GL lighting, are no longer a part of the API. But the flip side to that is it really puts a lot more power in your hands, because the era of GPU programmability is now going to be a part of the handheld API. And as I've mentioned earlier, it really is a convergence of features between desktop and handheld. So what I'll talk about now is how shaders fit into the OpenGL ES pipeline. So the picture here is a diagram of the fixed function OpenGL ES pipeline for 1.0 and 1.1. And so the first orange box, which is the transform and lighting stage, is now going to be replaced in ES 2.0 with Vertex shaders. So all of the things associated with fixed function transform and lighting are now going to be done in the Vertex shader. Likewise, the other orange boxes, the texture environment, color sum, fog, and alpha test, are all going to be replaced with Fragment shaders. And what I'll do now is talk a little bit about each one of those shaders and give some examples of what they look like. So first of all, let's look at the Vertex shader. The Vertex shader takes as input a set of vertex attributes. And this is basically data that varies per vertex in your object, such as position, normal, texture coordinate, tangent, binormal, that kind of data. And that gets fed in as input to the Vertex shader. In addition, the Vertex shader can read from a set of uniforms, and this would typically be loaded with things like your matrices or lighting state, that type of thing. Additionally, for implementations that support it, you can fetch from textures in the Vertex shader. And the Vertex shader produces as output a set of varyings. And these are the outputs that are going to be read as input in the Fragment shader that will be interpolated across the primitive. In addition to the user-named varyings, you have two built-in varyings, GL_position, which every Vertex shader must output, and that's your transformed position, as well as GL_point size, which is used for the rendering of point sprites and specifying a size per point. So here's some example source of an ES Vertex shader. The first token at the top is just a version token saying we're version 1.1 of the ES shading language. We then have two attributes, which these are the per vertex inputs. We have a 4-component position and a 2-component texture coordinate. We then have a uniform matrix named transform, and the application would typically load with the equivalent of the model view projection matrix. And then the outputs of the Vertex shader are the two varyings. There's a 2-component texture coordinate that will be passed to the Fragment shader, and GL_position, which is declared to be invariant, and I'm going to talk a little bit later in the talk about what that invariant keyword means. And then we see a very simple shader that basically just multiplies this transform matrix by the input vertice and passes the texture coordinate through to the Fragment shader. So now that we've gone over the Vertex shader, let's take a look at what the Fragment shader looks like. The varyings that you output in your Vertex shader are going to be read as input in the Fragment shader. In addition, there's some other built-in varyings, GL_front facing, which you can use to determine whether you're rendering a front or back face, the Fragment coordinate, which can be used to determine the window position, and point coordinate for texturing point sprites. In addition, you can also read from uniforms in the Fragment shader just as you can in the Vertex shader. And of course, you need to be able to sample from textures. And from the Fragment shader, we output a final fragment color, which will ultimately be used in the frame buffer step. So let's take a look at what an example Fragment shader looks like. Again, we see the version token, a sampler, which is declared to be of type 2D, which will be bound to a 2D texture. The texture coordinate that we'd output from our Vertex shader is read as input in the Fragment shader and interpolated across the face. And then we have a very simple Fragment shader that does a 2D texture fetch from the sampler and outputs a final fragment color. So this is just a very simple Fragment shader. Obviously, there's a lot more that you could do here. So with that said, what I want to talk about now, we've kind of done an overview of how shaders fit into the ES 2.0 API. And what I want to do now is look at what's changed in the GL shading language relative to desktop OpenGL. So the first change is the addition of binary shaders. So for those of you familiar with desktop OpenGL, when you compile a GLSL shader in OpenGL, you send in a string of source into the driver and you ask it to compile and link it. But when you think about what the driver is actually doing there, it has to have a full parser, compiler, optimizer, and linker. And that's a very large piece of software that doesn't necessarily make sense to exist inside of a driver on an embedded device. So what was introduced for ES 2.0 was the notion of binary shaders, which allows for offline shader compilation. Essentially, any vendor, such as ATI, would provide a tool to the developer which will take these GLSL shaders in as input and output a binary format which will contain the final compiled code. One thing I want to mention about binary shaders is that this is an optional feature. Basically, the way the spec is written, a driver must either provide an online compiler or an offline compiler, or both, but it has to support one of them. But typically, you'll probably be doing your shader compilation offline because it will improve load speeds and also just generally be more efficient in terms of memory usage for the driver. Another thing that's changed is that in desktop GLSL, you could link multiple Vertex and multiple Fragment shaders together to simplify things for ES implementations. You now have just one Vertex shader and one Fragment shader. And in addition, you can now load a binary shader pair. So not only can you compile an individual Vertex or individual Fragment shader offline, you can link those together offline and just load the binary pair so that the offline tool can do all of the work. In terms of the language itself, we'll talk about some of the things that have changed in that. All of the built-in attribute variables that existed in desktop GLSL have been removed. So for example, you had GL_Vertex, GL_normal, which were semantically bound to the Vertex pointer, the normal pointer. Well, in ES, there's no semantic bindings. Everything is simply a generic Vertex attribute. You can send in whatever data you want as Vertex attributes and use them however you want. In addition, all of the built-in varying variables have been removed. So in desktop GL, you had outputs that were bound to, for example, the GL_texture coordinate. Those don't exist in ES GLSL, although there is one new varying for outputting the point size. The last item here is that most of the built-in uniform variables have been removed, and this is really probably the most significant of the changes. In desktop GLSL, you could ask the driver to give you any of the state from the GL. For example, if you wanted the model view projection matrix, you would simply say, I want to use the GL_model view projection matrix. But none of that state exists anymore. There is no matrix stack in OpenGL ES. Everything must be done by the application. So essentially, you need to declare your own uniform matrices and be responsible for computing model view matrices, projection matrices, and loading those to the shader. So this is probably one of the biggest places that it places more burden on the application. Some other things that have changed are that 1D and shadow texture functions have been removed. In addition, some of the more complex operations like noise and derivatives have been made optional. An ES implementation is free to support them, but it doesn't have to. In addition, the F-transform operation was removed. Just for review, for those of you not familiar with it, F-transform is a function that if you call in desktop GLSL will produce a position that is guaranteed to be invariant with the position produced from fixed function processing. Well, since there is no fixed function, it doesn't really make any sense to have F-transform anymore. But you do still need the ability to be able to have two shaders be invariant with each other so that you can do, for example, multipass rendering. So what was added for ES to enable this is a new qualifier, invariant, that you can put in front of any of your output variables from the Vertex shader. And if you do a computation into that output in two shaders, you're guaranteed to get the exact same results without any precision problems. So this is important for multipass rendering. In addition, another thing that was added to GLSL is precision qualifiers. So all of your variables, all of your temporary variables can now be declared with a low, medium, or high precision. And what this basically does is allow an implementation to do computations at a lower precision by which they can potentially have a smaller memory footprint, also consume less power, and execute the shader more efficiently. So there's three precision qualifiers, low, medium, and high. If you don't declare a qualifier on a variable in the Vertex shader, it will be, by default, float. There is no default for Fragment shader. That one's up to the implementation. In addition, there are queries that were added to the API that allow you to query what each one of these precisions actually means. So you can ask how much range and precision does low, medium, and high have. Another change was that the minimum number of Vertex attributes and uniforms were reduced. And this was just to enable hardware implementations that were smaller than on the desktop. In addition, fixed function user clip planes have been removed. You can still do user clipping in the shader, but there's no fixed function user clip planes anymore. So we've talked now about how shaders fit into the ES API, what's changed in the GL shading language. What I want to do now is talk about what's changed in the API aside from the shading language. So first of all, let's talk about what's new, what was added for ES 2.0. First of all, there are new vertex and attribute data formats. Two of them are the fixed data type, which is a signed 15.16 fixed point value, which can be useful on implementations that don't have a floating point CPU. In addition, there's a new optional vertex type half float. This is the same one that we have in DX on the desktop, which allows you to compress your vertex data into half the size of a normal float. In addition, there's a new compressed texture format, Ericsson texture compression. This is a block texture compression format, an RGB compression format that has the same compression characteristics of DXT in terms of the size, although it uses an algorithm that in some cases can yield better results. If you're interested in the algorithm on that, look up some papers on iPacman. Ericsson based their implementation on the research that was done for that. In addition, there are floating point textures were added to the API, so you can have 16 and 32-bit float textures. These do exist as an extension in desktop OpenGL, but they haven't yet been added to core. For ES 2.0, they were made part of core. Continuing with what's new, frame buffer objects were added to the core API. So again, this is a feature that exists in desktop OpenGL, but currently only as an extension named ext frame buffer object. And the extension, if you're familiar with that, the implementation for ES is very similar. They've added a couple of restrictions. For example, you can't render to individual MIP slices, and there are no multiple render targets or accumulation buffers, but by and large, it's the same basic API. Another thing that's been added is the shader precision query. I mentioned this earlier. This query allows you to find out information on how much range and precision there are for each of the low, medium, and high precision qualifiers. And in addition, there's a new entry point for loading binary shaders. And this is used for loading offline compiled binary shaders that I mentioned earlier. So that's what's new. Now I want to talk about what's been removed from the API. So the first thing that's been removed is the ability to enable and disable multi-sampling in the middle of rendering a frame. There is still multi-sampling, but the way it's enabled is by requesting a pixel format from EGL that has multiple samples. In desktop GL, you could enable and disable multi-sample at any time, and this caused a lot of headache for driver writers because they essentially had to do a multi-sample resolve in the middle of rendering a frame. So there's no more ability to do that, but you can still do multi-sample rendering. In addition, anti-alias lines and points and anti-alias points were removed. Again, this is because those are features that have caused desktop driver writers a lot of headache and tend to not be really used that much by games. There are still point sprites that are supported, and in fact, they're a little bit more feature-rich than they were in desktop GL. Another thing that's gone that I've mentioned earlier is, in general, the fixed function pipeline is gone, and this means there are no more coordinate transforms or matrix stack. So any of the things you're used to with GL load matrix, molt matrix, all of that has been removed. And finally, occlusion queries, which were part of core desktop GL, have been removed from the API, although an implementation is still free to expose it as an extension. And lastly here, we'll talk about what features are optional. So the ability to map and unmap a vertex buffer object has been made optional. There were some vendors who had difficulty returning back system memory pointers to vertex buffer objects stored in local video memory. So that'll be exposed as an extension. In addition, 3D textures were made optional. It's a little bit questionable how useful 3D textures are on such small devices with a small amount of memory. Non-power of 2 textures are optional, as well as some of the features I mentioned earlier, the half vertex attribute data and the floating point textures. Okay, so we've talked about what OpenGL ES 2.0 is, what's changed about the shading language. What I want to do now is talk about what all of this means for writing games for OpenGL ES. So let me just stress this again. Fixed function is dead, it's gone. Your game engine now has to manage a lot of things it didn't used to have to manage. All of the computations related to computing matrices, the equivalent of your model view and projection will have to be done by your application. In addition, things like setting up the frustum projection and any of the things you would normally find in a constant, such as per light properties, fog properties, all of that is going to have to be managed now by your game engine. So how do you go about doing this? There's certainly a lot of different ways. One option that I'll mention that you could do is implement a fixed function wrapper. So while it's true that ES 2.0 has replaced fixed function with GPU programmability, it doesn't mean that you can't still implement the features that you're used to in ES 1.x. There's nothing stopping a developer from implementing all of the GL functions that you know and love in a wrapper on top of ES 2.0. Now, this may not be the most efficient way of doing things, but it is a way to maintain portability with older versions of the API. Another option is to create a custom solution, and I just wanted to mention the solution that we've worked on at ATI on the demo team. Basically, what we did was we created our own effect file format, and we manage all of the constants related to the camera, to lights, all of these things in our engine. And this allows us to target a lot of APIs at once. We have an engine that basically supports D3D10, D3D9, OpenGL, and ES 2.0. And by writing an engine that does not rely on fixed function at all, you can really cover all of the APIs that you need. So that's one possibility. Another thing I wanted to mention was with regard to lighting. So all of the lighting computations that used to be enabled by fixed function GL now have to be shader based. One option you could do is simply implement the GL lighting equations in your shader or do custom lighting equations. And if the idea of digging through the GL spec to figure out what the lighting equations are scare you at all, one piece of advice is to check out a tool called ShaderGen by 3D Labs. And basically this is a tool that you can select a bunch of light properties, if it's a directional diffuse light, and it will actually generate GLSL shader code that you can directly compile that will implement the lighting equation just as desktop OpenGL would. And really, this is actually what's going on in desktop GL drivers. Essentially, we look at fixed function state and we translate it into shaders underneath the hood. And this is just sort of exposing it to you to figure out what drivers are doing. So another thing I think you want to consider in developing a game engine for ES 2.0 is the notion of effect file formats. So there's more than just the management of shaders and constants. You also want to be able to manage things like render state, material properties, having techniques for rendering with multiple passes, binding constants to data in your engine, binding vertex attributes in your stream to data in your vertex data, as well as binding to textures. All of that stuff you're going to need to do now in your engine. And there's several options for how to go about this. The first one I wanted to mention is Collada FX, which Collada FX is a subset, or is a part of Collada, another API created by Khronos. And it's an extensible file format that allows you to create effects for multiple APIs, including OpenGL ES, both fixed function and shaders, as well as other APIs. So I definitely recommend checking that out if you're looking at a solution. And there's a talk, I believe, at 4 later on in this room about Collada, where I believe they'll be covering some more about this. And another option, again, is a custom solution. At the time that our demo team was considering developing an effect file format, Collada FX wasn't finished yet. So what we did is we created our own effect file format, with our own Lex and Yak parser and backends for all the different APIs. It's a very similar format to D3D's .fx format, but we made it much more cross-API friendly to support all the different shading languages that we needed. Another thing that I wanted to mention, if you are new to shader development and you're looking towards developing games for ES 2.0, is to keep in mind that there are just a ton of tools and examples out there for shaders. They've been around on the desktop for a while now. ATI provides a tool called RenderMonkey, which has support for the GLSL language. And we're also planning to add support for OpenGL ES 2.0. So this is free on our developer website, and definitely a great place to get started with shader development. There's a lot of examples of advanced shader techniques that you can easily use in your games. And of course, there's a lot of other shader tools out there from many different vendors who I'm sure will be presenting at GDC this year. So just to summarize things, we've talked about the overview and history of OpenGL ES and kind of looked at the evolution of the API and how we've gotten to ES 2.0. We've covered the technical details of ES 2.0 from a few different directions. We've looked at how shaders fit into the API, what's changed in the shading language, and also what's changed in the API relative to desktop OpenGL. And finally, I've given you some hopefully useful advice to get you started on how to develop ES 2.0 games. So just to conclude things, I want to stress that ES 2.0 really represents an exciting time to be developing games for the handheld platform, because we're going to see a true convergence of the types of programmability and effects that you can do on the desktop on handheld devices. But with that said, I do put some thought into how you want to design shaders into your engine, because it is a fairly significant change and will require some re-architecting of your fixed function engines. But with that said, if there are pieces of OpenGL ES 1.x that you found useful, it is possible to wrap that on top of ES 2.0, so implement the fixed functionality that you need. And finally, leverage existing solutions. There's been a lot of work done in shader development on the desktop. Look at the effect file formats and the tools and try to leverage that on your engines for handheld. Finally, if you are interested in more info, check out Khronos.org. You can download the ES 2.0 and shading language specs, as well as a lot of presentations on ES and the latest news. So that's all I had, and with that said, I think we have about 10 minutes left if anyone has any questions. No, we do. So the question was, does ATI have, did you ask a graphics chip or implementation of ES 2.0? The answer is we don't yet. I don't have any specific details on it. The only thing I can say is, ATI was, Affy Munchie, one of our architects, was one of the spec editors for 2.0, so we were actively involved in it. After the spec was released, we did announce that we intend to support it as an API, but we don't have any specific announcements as far as hardware goes. Any other questions? No. So the question was, is the binary format used for the binary shaders shared between all of the vendors? And the answer to that is no. It's a vendor-specific opaque format. The only thing that the ES spec mandates is there's a token, a vendor-specific token that you put at the beginning. Beyond that, vendors are free to do whatever they want. And I'm sure the reason you're asking the question is that that has implications for portability. It means that if you develop a shader and you compile it in ATI's binary offline tool, there's absolutely no expectation that that shader would run on somebody else's implementation. So it means that using the binary tool, you'll have to develop specifically for that platform. Any other questions?
That software that will be for mobile devices, can you make the games on the software emulate on the device, or we have to wait for the hardware?
So the question was, I believe, is it possible to emulate OpenGL ES 2.0 in software, or in order to develop with it, do you need to wait until there's hardware? The answer is that there's nothing stopping anyone from implementing ES 2.0 in software, and it may be done. I know, for example, that Hybrid has implemented ES 1.0 and 1.1 in software for many devices. I don't know if they have plans for ES 2.0. But I would imagine there probably will be development environments, perhaps on the desktop or something, before actual handheld devices. But I think having a software ES 2.0 implementation on an actual device and writing a game for it would probably not be that useful, just because it's running actual shaders in software, I think, would just not be fast enough. That's my guess. Other people might have different views of that. So. Yes?
How do you ensure that 1.1 games will work on devices with 2.0 hardware?
So the question was, how do you ensure that 1.1 games will run on devices that have ES 2.0? And the answer to that is what Khronos has done with 2.0 is they've now basically almost forked the APIs, and there's actually a different .lib and .dll that you would provide for 1.x and 2.x. So what's most likely to happen is that hardware vendors will provide 2 drivers for each platform, a 1.x one to run old content and a 2.x one for new content.
So you imagine that the graphics hardware IP provider would provide that extra DLL?
I guess to put it, the Khronos certainly allows that, and that's the way it's designed. I don't know that everyone will, but they're certainly free to do so. And if they have to maintain backwards compatibility, I don't think they'll have a choice. So, anything else? All right, well, thank you very much. I appreciate having the opportunity to talk to you, and thanks again.